The last talk of the meeting will be given by our friend Letterio Gatto from Politecnico of Torino, and the title is Giambelli's like determinants from endomorphism of exterior powers.
Thank you, Pietro. I'm very happy to be here. For me, besides being an honor, it's a pleasure to stay here to honor the birthday of Fernando. I think that I met physically Fernando for the first time in 2005 when we were going to Paraty. Yes, but for me, Fernando was a kind of spiritual entity because I began to work on topics. He was, I can say that he was a pioneer when he was investigating the loci of spatial bias transpoint in the moduli space. And his influence was so deep that in a joint paper with Eduardo Esteves, we have, Eduardo and myself, we have defined the spatial virus transpoint of Cukierman type. And then all the paper was about spatial virus transpoint of Cukierman type in opposition to those of Dietz type, okay? And, my talk may seem not completely in the framework of this meeting, but on the other hand, these Giambelli's like determinants are an output of something that I learned from the paper by Fernando, because I think that my first experience with Porteous formula was from reading to the papers of Fernando, and Giambelli's formula, as Kempf and Laxov pointed out, were generalization of the Thom-Porteous formula for more general maps of vector bundles to compute the general loci. So then, thanks to organizer to have invited me, and thanks to Fernando for the nice friendship we had along all these years. Okay, so I did a couple of pictures of foliations in spite I don't understand anything. That is the thesis by Fernando, that Fernando still forgot to sign for me. Yeah, you should sign it. Okay. Well, this is about recent work with Malieh Yousafzadeh of the University of Isfahan in Iran. And she is a big expert in representation theories of superalgebra, something I don't understand very well, as many other things. But here is the outline of the talk. In the first part, I will give an introduction, a pathway, motivation, what we do, and I think is the most important part of the talk, the techniques you can forget. Then the setup framework with the statement, where you will see depicted this Giambelli-like formula I was alluding to in the title, and the appendix, an appendix on foliations, on what I understood about foliation. Part one, introduction, and then the exterior algebra. Now I want to explain what we want to do. We take a vector space of dimension n, we consider the exterior algebra, and this is a vector space which has an algebra you can attach its algebra of endomorphism. And it turns out that the algebra of endomorphism of this exterior algebra is a Clifford algebra, whatever that means. We don't use now, but it's a Clifford algebra, Cn. I mean, it's a Clifford algebra spanned by the words you construct by using elements of the basis of Vn and of the dual basis of Vn. So you take words. I will be more precise in a while. And you see that the exterior algebra is a graded algebra. Indeed, has two kinds of graduation. As all of us know, the exterior algebra is the first example, easiest example of superalgebra. It has a Z2 graduation. But I'm thinking more in the graduation as a direct sum of exterior powers. And the homogeneous endomorphism means that you send the R exterior power to an R plus L exterior power. And it amounts, giving a homogeneous endomorphism of the exterior algebra, amounts to give a family of vector space homomorphism between the exterior power. And there is this observation. This is well known. The R exterior power of Vn is isomorphic as a vector space with the cohomology ring of the Grassmannian parametrizing R-dimensional vector subspace of Cn. This is not very relevant for the talk because we will use more formally, but that well-known is a kind of polemical because it is well-known because I wrote this in more than 10 papers, even if it is not yet in the DNA of the common mathematical, in the mathematical community. Anyway, what? Yeah, but it's too difficult. I know this, but this is too difficult because the reason why there is this isomorphism besides the Satake correspondence is the fact that both vector spaces have a basis parameterized by the same set. I mean, and then I think that Satake is slightly difficult for this. But I know that it is I have here, there is Antonio Nigro, who is an expert of the Satake correspondence for this kind. So then, what is our goal? To describe the induced homomorphism between BRN to BR plus LN. You see, BRN is isomorphic to wedge RVN, and BR plus LN is isomorphic to wedge R plus LN. And why? The why is that, for instance, if you take the space of n times n matrices, this n is very important because what I want to do is to propose a uniform presentation for n being either finite or infinite. Okay? So you can take the space of n times n matrices, and it may be regarded as a subalgebra of the Clifford algebra of homomorphism of degree 0. I mean, if you take a homomorphism, a matrix, n times n matrix, this defines a homogeneous homomorphism of degree 0 of the exterior algebra. Then BRN is a GLNQ module. This is something that I studied with Saleyan. The fact that BRN is a module over the Lie algebra of n times n matrices with rational coefficients is rather obvious. What is maybe more tricky is to describe precisely the module structure. And if R is equal to 1, this module structure is nothing else than the matrix multiplication by a vector. If n is equal to infinite, we get a finite type versions of vertex operators. So what I mean is that when we think to the vertex operators, it is not important for most of the audience to know what vertex operators are, but there are some operators arising in representation theory of infinite dimensional Lie algebra, and you have a bosonic representation and a fermionic representation, we will see in a while, is something very, not that, that difficult in our elementary context. And then you, sorry, and then you can fill these vertex operators already in finite dimensional situations. And if R is equal to infinity, one obtains the so-called bosonic vertex operator representation of the Lie algebra GL infinity Q due to Date, Jimbo, Kashiwara, and Miwa. Sorry. Now, this is, I think, one of the most important slides of the talk, because I show you what I want to do. Thank you. I think. So you take this matrix, a 2x2 matrix with these indeterminate entries, and you can regard this matrix as the generating function of the elementary matrix. Eij is the matrix having all 0 but 1 in position ij. And then that simple matrix can be seen as a generating function of a basis of a GL2Q. And then we consider vector space of dimension 1, Qx modulo x squared. You have the basis 1 and x. And out of this basis, you can construct the generating function of the basis 1 plus xt. T is a formal variable which encodes the basis, the information about the basis of this space B12. What we do, sorry, this I say, then I take, sorry, no. Then I take the matrix 1 w minus 1 z w minus 1, and I multiply by the vector 1t. I perform the computation, and then I can define a polynomial e z w t, which is the output of the multiplication of the matrix by that vector. You get this 1 plus t over w plus x. X is the basis element. Z plus tz over w. And what is this? This is what we can call the structural polynomial of the action of the matrices on, or the 2x2 matrices on the vector space of dimension 2. And you see that the property of this structural polynomial is that if you want to compute the coefficient of z to the power I, w to the power minus j, and t to the power k of that polynomial, you get precisely the output of you get by multiplying the elementary matrix Eij times the element xk of the basis. Of course, if k is only 0 or 1. If you want to compute the multiplication of Eij times x2, you would get 0, because there is no x2 in that polynomial. What is the inspiration of this? The inspiration dates back to 1983, when Date, Jimbo, Kashiwara, and Miwa showed that the polynomial ring in infinitely many indeterminates is a representation of the Lie algebra of all the matrices indexed by the integers with a finite support. I mean, all the elements 0 but finitely many. And again, we can consider a huge matrix, ziw minus j, which we understand as the generating function of the elementary matrix. And what we do? We take a polynomial, qx, okay? And I want to multiply by that matrix. And there is a very nice, at the first sight, mysterious recipe, because you take a polynomial, and then you act by means of the exponential of these differential operators. You see, I mean, you are involving infinitely many partial derivatives, and these, when you act on Qx by means of this exponential, you multiply by these other formal power series. And what you get is that once you apply this rule, when you apply this rule, if you want to know what is the multiplication of Eij times the polynomials, is just taking the coefficient of Zi, or W minus J, of the second member of that expression. The DJKM phenomenologies have been variously faced in the literature, in the theory of solitons, for instance, KDV, Kortewé-de Vries, Kadomtsev, Petiashvili, universal Grassmann manifold by Sato, in connection with the vertex operator representation of affine Lie algebra, the milestone paper by Katz, Lepofsky, Wilson, where you can see how they use systematically vertex operators to study a representation of Katz-Moody algebra. Also Brazilians worked quite a lot on vertex operators. I just cite a paper by Cox, Futorni, Tirao of 2013. Then we have a milestone paper more related with what we are talking about, a milestone paper by Bloch, Kounkov, the character of the infinite wedge representation, 1997. And Vera Serganova, who was also a collaborator of my collaborator, Malie, Penkov, Frenkel, who worked on categorification of boson fermion correspondence, Licata, Savage, and so on. So, what is, let me only this, that we wanted to understand the last formula, and what we contended with my collaborators is that this formula is nothing but an extremal case of a very general situation. The other extremal case is multiplication of a matrix by a vector. This is. And so the goal of this talk would be to try to present a general formula encoding all the case for any n, and ranging from 1 up to infinity. Okay, then there is this, So there is this remark by Bézac, Contiero, and Martins, Journal of Algebra 2022, that they say, well, it is easier, instead to, even for the date Jimbo Kashiwara-Miwa, instead of constructing the generating series of the action of elementary matrix, study the generating studying the structural power series of the action of the Lie algebra GL infinity over the polynomials. So the idea is not just looking the action of Zi W minus J over one basis element, but you take all the basis elements at once, and we will see in a while that if you define PIT as the sum of the power, the ith power of the variables, new formal variables, T1, T2, and so on, you get that exponential is precisely the generating function of the basis of the ring of polynomials in infinitely many indeterminates. So now, this is the setup. the setup, we have, now we fix the notation, Vn for us is Qx modulo Xn, and we are, I mean, if n is infinity, it means that the relations get higher and higher degree, so V infinity is nothing but Qx. And then, as it is customarily, we denote by delta J the dual basis. Delta Jxi is equal to delta Ji. So nothing really difficult up to now. Exterior powers, I don't need to say anything about exterior algebra, exterior power. Just remember that the exterior powers are, have a basis parameterized by partition of length at most r, whose Young diagram is contained in n times r, in n minus r times r rectangle. The reason of this slide is more for fixing notation. I take a partition lambda by x underline r lambda. I mean that element of the basis of the exterior power. And you see that I use a decreasing notation for considering the basis element. And XR0, it means the basis element associated to a partition of degree 0. And this plays the role, I mean, if R were infinity, this would play the role of the vacuum of charge 0. Exterior algebra, this is, we know what is the exterior algebra. This is the direct sum of the exterior powers. And then in exterior algebra, as we know, we have an endomorphism as a Q-vector space endomorphism given by wedging to each U. To each V U, you can associate a V wedge U. And, well, these formulas are very standard. And there is the contraction. Here there is a small formal novelty, because if you take alpha, a linear form, it acts on wedge Vn by contraction. This is, everybody knows what is a contraction, especially people working in foliation. You are contracting an exterior vector by means of a linear form, and you can use that diagram. That diagram is very useful to do computation. This may sound incredible, but to do explicit computation, even if n is equal to infinity, is very useful. And this diagram means this. For example, if you take a linear form and you want to contract, you want to contract U1, U2, wedge U3 against this linear form, you can consider this table, this array, which means just like the expansion of a determinant, alpha U1 times the exterior, the wedge product of the two vectors you have by deleting the first row and the first column, and then minus alpha U2, U1 wedge U3, plus alpha U3, U1 wedge U2, and it is very useful for computation. And this, I wanted to point out this. Now, if we take two multi-indices, I and J, each word, here is where the Clifford algebra came out, each word, xi1, xih, delta j1, delta jk, acts on the exterior power, wedge r Vn, mapping to wedge r plus h, which is the number of how many times you are wedging with x, minus k, which is the number of how many times you are contracting with delta, where xi delta j applied to u means just this. You take u and you start contracting with delta jk minus 1, iterate the contraction, you get an element of wedge r minus k, and then you you wedge h times with the x. And if u is equal to u1, wedge u2, wedge ur, then using the notation, you remember that our convention to write the contraction is just this diagram. You may wonder what this diagram means. It means just that first you contract with delta jk, and you write, or delta j1 maybe, you use that diagram, then you get a vector of degree 1 less in the exterior algebra, and then you contract once more, and a bit of combinatorics gives you this expression, which can be written also in this way. Look. Oh, sorry. Okay, so this expression can be written this way. I mean, with the same convention, you erase one column, one row, and then you wedge what is remaining. And this is a diagram which is very useful, which can be written as a h plus k determinant in a way we will see in a while. Okay, this is something not very difficult, but of course you must get used to that. Okay, sorry. What? This is not a determinant yet. This is not a determinant yet, but it will be made into a determinant, but it's not a determinant. Thanks.
That's just notations.
Yeah, this is notation, which is, yes. Then I want to say a Q basis for BRN. This is very well known. I denote the basis element by S lambda, which for people who are acquainted with Schubert calculus means that we are using sure determinants in the Segre class of the tautological bundle. And then look at the definition I give of this basis element. Sorry, this may seem involved, but you take the exponential of xi pi tr summed. Pi are the power sum, t1 to the power I plus t2 to the power I plus dots tr to the power I. Then you multiply by the van der Monde, and you take the coefficient of t1 r minus 1 plus lambda 1. Okay, why I write the basis in this way? Just because I want to work with all the basis elements at once. All the basis elements at once are encoded in that exponential. I want to use that exponential because I want to consider all the basis elements at once. And there is the famous Jacobi-Trudi formula saying that S associated to a partition lambda is nothing but that determinants associated to the same basis elements associated to partition of length 1. This is something really classical, nothing new. Nothing new. And then there is this theorem, myself 2005 and Laxoff and Thorpe 2007, 2008, that wedge RVN can be made into a BRN module generated by this minimal element, this element of degree 0 in the exterior power, such that the so-called Giambelli's formula, this is how also Laxoff and Thorpe called, Giambelli's formula holds. It means the following, that BRN acts on the exterior power in such a way when you take XR0, which is the basis element associated to the partition 0, all the other basis elements you can get by moving it, by acting with S lambda by that sure polynomials, that the determinant I showed you in the previous slide. So this is, again, something you must get used to, but people who have some experience with sugar calculus can recognize the Giambelli formula, because you can interpret this formula as keeping the fundamental class XR0. You can think of the fundamental class of the Grassmannian, and you cap with the cohomology class. So this is a kind a way to spell the Poincaré duality for. And then you see, sorry, this is something that I like to show, because look at this formula. There is XR lambda and S lambda XR0. And we know that there is this bijection. So at the end, the only relevant part is the lambda, is the partition. Because when you have a partition, you have a basis element of Brn, and you have a basis element of wedge Rbn. And that's why I depict this picture that I like very much, because I take the vector space over the rational generated by all the partition, and to each partition I can associate either an element, a polynomial, Br in R indeterminate, or an element of the exterior algebra, of the exterior power. And then, of course, there is a translation. You can go from the left to the right, and this yoga of going to the left to the right is what people called the boson-fermion correspondence. What we are saying is that, indeed, what we are doing is working on that Q to the power PR. We are working just on partition, and we have a twofold way to represent partition, and the way to pass from one to the other is the boson-fermion correspondence, especially if R is equal to infinity. If R is equal to infinity, is the classical boson-fermion correspondence. Okay, example. The example is this. The example is this. For instance, if you have X7, wedge X5, wedge X2, look. Imagine to put X5, X7, X5, and X2 at the last row of that matrix. But instead of writing X, you write S. And then you just complete to a 3 by 3 matrix by subtracting 1 at each row. S7, S5, S2, and then the second row, S6, S4, S1, and so on. So this is the Giambelli formula. Then, for all ij, well, there is an induced map of the exterior algebra. I don't want to insist on this, but part 3, statements and idea of proof. For the statement, I need 3 sets of formal variables, zh, z1 up to zh, wk to the power minus 1, which means w1 minus 1, wk. The reason of the minus 1 is historical. I mean, in representation theory, it is customarily using these kind of variables, and then we follow the tradition. And tr, other formal variables. The tr we will use to encode the basis element to construct generating function of the basis. The goal, again, is to describe the structural formal power series. That is a formal power series that, when you are looking for the coefficients of the formal variables, is giving you the result of the product of the element of the algebra for the element of the vector space the algebra is acting on. So this is exactly what I said. I want to produce an expression for ERHKN such that if you take that the coefficient of z to the power I, w to the power minus j, and I apologize for that. I translated in the previous slides, but this is the van der Monde multiplicated by T1, well, this is a sure polynomial, but it will be clear in a while because I don't use that notation in a while. So this is what I want to do. You see, the E would be the action of the general element, of the general word of the algebra of the endomorphism or the exterior algebra. Then there is that star. I want to define this action. And here is the theorem. I mean, the theorem is the computation of that ERHKN. And now we will see the determinant indeed. Look, the theorem is this. Exponential xi pi tr. Pi tr are formal power sums. Is the generating function of the basis of Brn, and then I want the action of this E on this exponential is given by this formula. You see, a product, I mean, a formal power series. There is that awful exponential, which is not that difficult to get. And, but there is the DRHKN we want to understand, and this explains the title, Giambelli, because this is indeed a generalization of Giambelli. For instance, if K were 0, K would mean the number of times you contract with the elements of the dual basis. This is the classical Giambelli's formula Schubert calculus. If H is equal to 0, I mean that you are not contracting, then you get a kind of dual Giambelli formula. But the best fun we had with my collaborator on this formula was not even to prove it, but to look at the special case, because putting H, giving special value to H and K, to R and to N, you cover all the cases, inclusive date Jimbo Kashivara Miva, inclusive multiplying a matrix by a vector. Okay, and then there is this S that should be defined. Now, main ingredients of the proof, and I will give you an example of that, that determinant in an easy case. You take, look, here is, everything is very easy. You have the endomorphism of Vn given by multiplication by x. Vn is a polynomial ring, is Qx modulo xn. So you have the multiplication by x. To the multiplication by x, you can consider the trace of the ith power of x. What is the trace? This is classical. This is the way I like more to spell the trace, because it's precisely the trace in the sense of the sum of the diagonal elements of a matrix. The trace of xi against w, where w is an element of, if w belongs to Vn, the trace is just xi times w. But you extend this expression trace xi using a Leibniz rule. In fact, I say the trace is the unique derivation of the exterior algebra, such that the first condition says that it is a derivation of degree 0, the second condition that is a derivation. And the nice of this derivation is that being a differential operator of order 1, you can write this sigma plus z, this formal power series. Look at the exponential at the second member. It looks nasty, but it is not, indeed. This is also called the platistic exponential. But we don't need really to know that explicit expression, even if it was fun to find it. What we want to know is that the sigma plus z is an algebra homomorphism. An algebra homomorphism because the exponential of a derivation gives an algebra homomorphism. And as an initial condition, and the initial condition is that the sigma plus z xj is the series xi plus xi plus 1 z plus xi plus 2 z square, etc. And the reason why we call sigma plus because there exists sigma minus as well, even if we didn't touch that. But the reason we write sigma I is because it's a tradition to denote the special Schubert cycles in the Schubert calculus by sigma I. So what I want to do to say that we could interpret that exponential as the Chern polynomial of the universal quotient over the Grassmannian. This is all written. I mean, it's not simulated. It's not simulated. And look the yellow bar. Look at yellow bar. This is that exponential. If you put a minus, you get the inverse. And the inverse is the unique Q algebra homomorphisms. I wrote what is an algebra homomorphism such that now, when you act on the element of degree 1, it's just xj minus z times xj plus 1. You can check that they are inverse of one another in the ring of formal power series with the coefficient and the endomorphism of the exterior algebra. What? Yes, thank you very much. Thank you very much. Thank you. Fact. This fact. If you, you take this element of the exterior power, which is the basis element associated to the partition of weight 0, and you act with the sigma plus TR, is a variable, TR, and then you act with the sigma plus TR minus 1, and then sigma plus T1, what you get is XR lambda multiplied by T1 R minus 1 plus lambda 1, etc. Multiply this. That is, the product of the sigma gives us the generating function of the basis of the exterior algebra. So we have, and compare with this, it's the same. It's like the diagram with partition going to B going to wedge R. It's the same thing. Now we have a perfect vocabulary. So when we want to compute the bottom part, we compute the top part, because in the top part we have just to use Leibniz rules. It's easy. Compare, and then the idea of proof. I have 3-4 minutes for the proof. I propose you the case h equal to k equal to 1 and r equal to 2, for instance, for the Grassmannian G to 4 if n would be 4, but I take n equal to infinity because for n equal to infinity, all the subject is much easier. The hardest part of our work was to cope with the case in which n was finite. And also R was finite. And then we want to compute that matrix, ZIW minus J, against a generating series of the ring B2. B2 is a ring of X1, X2. There should be also X3, X4, but xi for I bigger than 2 is a polynomial in x1, x2. Anyway, you want to compute zi w minus j against xi tensor delta j, which would be the elementary matrix. And you see, there is that star because we are acting with the wedging and contracting on a polynomial. How you can do that? You wedge and contract with the element of the exterior algebra. Then you translate the problem of the exterior algebra. Now I act with the sigma plus z x0 wedge contraction with delta W minus 1, which is a generating function of the contraction operators, with the generating function of x1, x0. Well, you use our notation for writing a contraction, and you get that pseudo matrix there. In this case, is indeed the determinant because it's just a 2 by 2 matrix. There is a technical step which permits you to simplify the first row in U1W, paying the price of multiplying by that exponential. Then everything is made explicit. I'm sure that you are not that interested to follow all the steps, which are easy indeed once you have some familiarity. And look at the result. I mean, you don't need to work hard for finding the result. Those bold S are written explicitly in the last expression. You see, in this idea of proof, I compute this expression by hand. But what I'm saying is that you can find the same expression specializing the general determinant formula I showed you before. Okay, and then, well, the idea of the proof, what is the idea of the proof? You have to use the vocabulary. The vocabulary that the generating function of the Schur polynomials, of the Schur basis of a polynomial ring, can be translating in the generating function of a basis of the exterior power. Okay. An appendix, I know nothing about foliations, but I felt a little bit shy to participate to a meeting devoted, besides than Fernando, to foliations. And then I tried to think something I could say, maybe with the same spirit of a joke. Oh, sorry, I'm uncovering my cards. So, which foliation are mildly related with the subject? Probably what I'm going to say does not make sense, but the pictures are nice. The ring, the polynomial, this is something very nice, that the cohomology ring of the Grassmannian, I tensor by C because usually I use with Q coefficient, can be expressed in this very nice form. C x1, x2, xr, modulo dxn plus 1. You say, but where are the other variables? Is that xi are the Newton power sum. So you have all, for each n you have some Newton power sum, but when Newton power sum in what? In the Chern roots of the quotient bundle. So then you discover that xr plus 1, xr plus 2 are all polynomials in x1, x2, xr, and then you can write the cohomology ring of the Grassmannian in this form. It means the relations are encoded in requiring that differential is 0. And then I try to write picture, because if dxn plus 1 is equal to 0, xn plus 1 is equal to constant. And then I let the constant varying, and you get, I think that y24 is wrong spelled. It's not spelled in the correct way. But morally, if you take the dx5 would be a one form derivative of x5 with respect to x1 plus derivative of xy with respect to x2. And then I wrote the level set of x5. x5 in function of x1, x2 is x1 5 over 20 plus x1, x2 square equal to c. You may argue, saying me that this is not a foliation, has nothing to do with foliation, but the picture is nice. This is for the Grassmannian G25, And then I did also the case of the Grassmannian G36, where you get a surface now. No? I mean, you get some integral, prime integral, which are surface. And then I want to provoke you by looking at the picture for the Grassmannian G35. We get again surface, but then you get worried because G35 would be G25. So why in G25 we have curves, here we have a surface? Just because in this case X3 is a polynomial in X1 and X2, so you should cut this picture with the polynomial expression of X3 as a polynomial expression in X1, X2. So these are the pictures I want to give to Fernando. And then happy birthday, Fernando. And now a non-official picture. Do you remember this picture, Fernando? I don't think you remember this picture. Was in the best restaurant of the world. And thanks to all the organizers for this beautiful and touching Fernando's party. Thank you.
Any question? Some remark?
I wonder which is the best restaurant of the world.
I can't say. Ask Fernando. I couldn't say this.
Any other interesting question about a five-star restaurant? Okay, since this is not the case, we thank again Letterio, and I join Letterio also to thank the organizer and all the participants and the speakers. And again, happy birthday to Fernando, and thank you, Fernando, for everything.